Edexcel Core Pure Calculus 4 Integration using partial fractions. Integrating where the denominator has the form ax plus b times cx plus d. It often helps in integration to rewrite the algebraic fraction in terms of separate partial fractions. We may need to check that the order of the denominator is greater than that of the numerator, so the denominator needs to have a greater order than the numerator in order to create the partial fractions. If not, then we may need to use algebraic division or other suitable methods in order to reduce the order of the numerator before integration can occur. The partial fractions allow us to split the integral into two or more separate, easier integrals. So here, for example, if we're integrating x minus 9 over x plus 4 times x minus 4, so here, for example, if we're integrating x minus 9 over x plus 1 times x minus 4, we would need to check that the order of the numerator was lower. So in this case, we have a linear numerator of order 1 and a quadratic denominator of order 2. So we've got order 1 divided by order 2, which means it's okay for partial fractions. We've previously found the partial fractions for this expression, and we discovered that they were 2 over x plus 1 minus 1 over x minus 4 dx. So this original integral can now be done as two easier integrals. So this first integral becomes 2 ln modulus x plus 1, so that's a fairly standard integral, as is the next one, which is ln the modulus of x minus 4, and not forgetting the constant of integration. Just using a power law to tidy this up, we can write it as the ln of x plus 1 squared, which strictly speaking doesn't have to have a modulus because it must be a positive quantity, minus the ln of x minus 4. And then I can use my log law to bring these logarithms together as the ln of x plus 1 squared divided by x minus 4 plus c. So the thing to remember here, once you've got your partial fractions, is that it allows you to turn this single integral into two separate integrals, both of which can be done as standard integrals, and then we've used a power law and the division law in order to get to the nice, neat final answer. So here, before we start thinking about partial fractions, if we look at the order of this problem, we've got something of order 2 in the numerator divided by something of order 2 in the denominator, so we've got a problem. We cannot put this into partial fractions as yet. You could put this into the correct form by doing algebraic long division, but quite a neat way of doing this is to take 5x squared over, expanding the brackets, x squared minus x minus 6. I could at that point do algebraic long division, or an alternative method is to say, well, let's keep this denominator expanded so it's clear, but instead of writing it as 5x squared, let's write it as 5 lots of x squared minus x minus 6, so it looks just like the denominator. We've still got our 5x squared, which we need, but we've created minus 5x, so we need to add on a 5x, and we've created minus 30, so we need to add on a 30. The advantage of this approach is that we don't have to do algebraic long division, and when I split this into two fractions, I get 5 times bracket over bracket is just 5, and the bit left over is 5x plus 30 over the quadratic, and at that point I would go back to factorized form. So the only issue we've got now is we've dealt with the quadratic divided by quadratic, so we've separated it up, and we'll deal with the 5 later. All we've got to do now is to take the 5x plus 30 over x plus 2 times x minus 3 and put that into appropriate partial fractions. We've got a linear factor in the denominator and another linear factor, so we could use constant a and constant b. So just to recap, we've got a numerator and denominator are both quadratic, so we have to either do the division, so you could do algebraic long division, or use the method that I showed you previously to write it as 5 plus this fraction. And it's that fraction that we would have to put into partial fractions. So if we focus on putting this into partial fractions, if I multiply through by the denominator, I get 5x plus 30 is the same as a x minus 3 plus b x plus 2. Looking for nice values of x, for example, when x is 3, we get 45 is 3 take away 3 is 0, and 3 add 2 is 5b. So we found b is 9. Another nice value of x would be x equals minus 2 because of this x plus 2 term here. So I've got minus 10 add 30, so there's a 20. Minus 2 take away 3 is minus 5a, and then a 0 at the end. So now we know what a is. A is minus 4. So now when we come to look at the original integral, which was 5x squared over x plus 2 x minus 3, that integral can now be turned into the integral of, don't forget, the 5 that we had on the previous slide plus these partial fractions. So we've got 9 over x minus 3, and we've got a, which is minus 4, so that's minus 4 over x plus 2. And don't forget that extra 5 that we had. You mustn't let that disappear. Now when we do the integrations, we get 5x plus 9 ln of mod x minus 3 minus 4 ln mod x plus 2. Then using our power laws to simplify these logarithms, it's ln x minus 3 to the 9 minus ln x plus 2 to the 4. And then we can bring these two logarithms together using our division law, so we get 5x plus the ln of x minus 3 to the 9 over x plus 2 to the 4 plus c. And there is a complete result for the original integral. So the things to remember here, we've already reduced the order of the numerator to linear before we go for these partial fractions, and then we look for nice values of x. So this term suggests x is minus 2, and this term here is suggesting x equals 3. So they are two good methods. Once we've got the partial fractions and we go back to the original integral, don't forget we need that plus 5 that we had from the original separation. So the integrals become easier. Don't forget the coefficient 9 and the coefficient 4 once you've done the two integrals. And then using your power laws, we can have x minus 3 to the 9 and x plus 2 to the 4 before we do the division. Okay, both answers are equally adequate, but sometimes you may get a question which is a show that, and examiners may want you to get it into that very neat, tidy logarithmic form to match the answer that may have been given in a question. So in summary, we should always check that the order of the denominator is higher than the order of the numerator before we look for partial fractions. If it isn't, then we may need algebraic long division or an appropriate method in order to achieve that. Then we split the algebraic fraction into its partial fractions, and the integral can also be split, and we can have separate integrals which should be fairly standard or predictable integrals to do. For linear factors, if there's a linear factor in your denominator, then you will be looking at logarithmic results, which can then be combined into a single logarithm if required or preferred. It's only really worth doing this if the coefficients are relatively simple. So as in the previous example, the coefficients were integer values of 4 and 9, which made the log laws relatively straightforward to apply. So in the next session we're going to be looking at integrating where the denominator has the form ax plus b cx plus d squared.